Good afternoon and welcome back to the session 6 called Nanotechnology for Air and Water Security. My name is Professor Mercouri Kanatsidis, and it is my pleasure to introduce our speakers, Professor Will Dichtel and Professor Omar Farha. Will Dichtel is the Robert L. Letzinger Professor of Chemistry. His research focuses on using the tools of synthetic and supramolecular chemistry to synthesize and develop structurally precise compounds, organic materials. The projects in the Dichtel lab involve organic and polymer chemistry, solution chemistry, and solid-state characterization of the and nanofabrication, and the comprehensive characterization of the discovered materials. His research interests include materials for water purification, energy storage, separations, new methods for recycling plastics, and expanding the control of polymerizations in the second and third dimension. Professor Dichtel earned his undergraduate degree from MIT and his PhD degree from the University of California, Berkeley. After that, he did a postdoctoral appointment, a joint appointment with Fraser Stoddard, our own Nobel laureate at UCLA, and Jim Heath at Caltech, before joining Cornell University as an assistant professor. And after that, he was promoted to associate at Cornell, and then we were fortunate to recruit him here at Northwestern in 2016. And since then, he has done spectacular work. He won numerous awards, including the MacArthur Fellowship and the 2020 National Laureate in Chemistry of Blavatnik Awards for Young Scientists. Omar Farha is a Charles E. and Emma H. Morrison Professor of Chemistry and the Director of Graduate Admissions at Northwestern, Northwestern's Chemistry Department. Farha earned his undergraduate degree and PhD degree at UCLA, and his PhD was honored with the title of PhD Thesis of the Year, Dissertation of the Year. Farha completed his postdoctoral appointment here at Northwestern, and in 2009 he became research professor, and he became full professor in 2020. And then a year later, he received the Charles E. and Emma H. Morrison Professor of Chemistry title. Professor Farha is an expert in metal organic frameworks, MOFs, as we call them, and his research involves solving a variety of problems in environmental science, in chemistry, material science, in applications in energy, and also in the environment, as well as national defense. He is also a co-founder and president of Nanotechnology, and he is the chief science officer of that company. He is also an executive editor of the ACS Applied Materials and Interfaces journal. So please welcome to the stage our session 6 speakers, Professor Will Dichtel and Omar Farha.
Thank you, Mercouri, for the introduction, and thanks to Chad and IAN for including us in this spectacular program, and for sure to the IAN staff for putting together such a wonderful event. It's second to none always every year. And for sure, we will miss Deb very much. She's been wonderful helping most of us here in chemistry department and many other departments who are affiliated with IAN. So far, you guys heard a lot of spectacular talks about how nanotechnology can play a leading role in health, in medicine, to solve really complex problems. Will and myself today, we get to highlight an area that most of us take for granted. However, it affects billions of people, and I will use the word billions of people, every day, and that's air and water. And put it simply, right now, air and water are more important than ever. because there is about 100 million people have struggled to get access to clean and affordable drinking water. About 7 million people per year globally die from pollution. And that's not it. We all know air pollution is the leading cause to what? Climate change. And if you think about climate change, very soon, we're talking about 2040. That's less than 20 years. We got to have more than 30 countries around the world struggle to have access to clean drinking water, which is something we think of when we wake up in the morning that should be giving that you have that clean water. Let's put it even closer to something we really know and see. It's in the news for the last few months, Lake Mead. I'm not even showing the picture what happens in June 2022, because at this point, there is hardly any water. So here, you could see in November 2000 versus in June 2021, how drastic. That's in the United States. Imagine what's going to happen if we stay on the same trajectory by 2040. So far, I told you, we are breathing really air, or a lot of us breathing air full of toxic chemicals. We are eating fish full of mercury. There is other people drinking water and bathing in water is full of lead. And the drinking water we get from our rivers and a lot of our lakes contaminated with a lot of chemicals. So at the end of the day, this is really an inadequate sanitation problem that we have to solve, and we have to solve this problem yesterday in order to save millions of lives per year. The only problem, as I said, when we all woke up this morning, what we did, we took water and air for granted. But I don't need to remind you that actually having an environmentally clean water, breathing air, clean air is your right, because it's really a health issue. And we talk about how we gotta solve cancer with nanotechnology. One way of solving cancer is not getting it from the beginning. And a lot of these toxic chemicals is one of the causes. And we cannot think of clean water and breathing clean air as a privilege, but it's really our right to do so. While we are doing it, Will is going to tell us how can we have our water and air safer to breathe and safer to drink, but at the same time, can we have a value added by capturing certain things from air and water?
All right. Thank you very much, Omar. When we talk about sustainability, whether we're talking about air or water, the theme is always circularity. And we, of course, are not going to be creating or destroying significant amounts of air. There's a lot of water on this planet, but a very small fraction is actually usable for our causes. And so when we start thinking about nanotechnologies and the kinds of solutions that we need in the future, we need to start thinking about air and water, whether they are pure or contaminated, as both a challenge but also a resource. And so in contaminated air, we have many, many sources of pollution, and we have to clean air in many contexts, whether it's particulates or volatile organic compounds. But we also need to look at air as the tiny sliver on this graph of all of the things that we can get from air as well. So carbon dioxide in this context is generally thought of as a pollutant, but it also can be, in certain contexts, a resource, particularly if it can be captured efficiently. There are even more trace gases in our atmosphere that are extremely important to our modern life. Helium, especially, to run MRI machines and in healthcare, other noble gases in the electronics industry, and many other uses. And as Professor Farha will tell you in a few minutes, even connecting the air and the water portions of this talk, most air has water vapor in it as well. And that can be thought of as a resource, particularly in arid environments. For water, the story is similar. We have a similar theme of circularity. And there are many loops. I can't even possibly cover them all in one slide, but I can give you kind of a 5,000-foot view here. We have a lot of fresh water, and we're sitting next to one of the most valuable freshwater resources in the world, in Lake Michigan. And whether we are taking usually already fresh water, or in certain cases salt water, we have to do a fair amount of treatment to that to make it potable for drinking or for industrial use or for irrigation or all of the other things that we use water for across humankind. Inevitably, when humans interact with water in those contexts, they contaminate it. Even when we are trying to be fairly good stewards of our water resources, this is inevitable to an extent. And a lot of what happens, at least in the context of obvious commercial, industrial, residential use, is that we send a lot of water through wastewater treatment plants. And those processes were designed to make water safe from the perspective of microorganisms. But they were not necessarily designed to really think of wastewater first as a resource, but also to remove all the contaminants that are necessary for us to really use water in the best possible way. So usually, wastewater treatment puts water back here, puts water back out into the environment, somewhat clean of microorganisms, but still with a lot of trace organic contaminants, and in many cases, a lot of valuable nutrients as well. So there are opportunities here. There are opportunities from wastewater, particularly rather than send wastewater out into freshwater bodies with lots of nitrogen and phosphorus in it, which then cause uncontrolled algae blooms. We can recapture that potentially, and we can use it in our own agricultural purposes. There are ways to close these loops, make them shorter and more efficient, and especially in arid climates, both in the United States and elsewhere in the world. There is a tremendous driving force and especially future development towards taking wastewater, further cleaning it to other purposes. And to do that, we need to do more cleaning. We need to remove trace organics. We need to remove certain salts and be able to close this loop without relying on having a nice source of groundwater or surface water available everywhere. And then finally, in our oceans and in our fresh water, we again have trace resources that are going to be very important for energy in the future, particularly lithium, uranium exist in seawater at very, very low levels. And it would change world politics if we could remove these well and efficiently. However, they're in a huge background of sodium chloride. And so this is a major, major separation challenge. All right, and so what do we do if some of these circular systems that are operating efficiently, if that's the goal, what do we need? Well, part of what we need are new materials. And in terms of a lot of really active research at Northwestern focuses on these materials that are designed for these types of purposes. So whichever one of those problems on the last two slides you might be interested in, generally speaking, it's possible to further discover and develop a material, particularly if you have control of materials at the nanometer scale, to be selective for whatever you're capturing. That's, I think, obviously important. You're going to need it to be high capacity. You're probably going to need to use it over and over and over again when we're talking about the scales of the air and the water problems. And it's going to need to be scalable, and we don't want to solve one environmental challenge and introduce another. And so the production of these materials really needs to also be environmentally friendly. So how does one think about this generally? Well, when we're talking about a storage or a separation problem, it kind of opens up a different paradigm in materials discovery, because materials chemists and polymer chemists and coordination chemists, we're all about structure, right? We're all about what chemical structure, what molecular structure, what maybe mesoscale structure can you build. And really, that's important in these materials, by all means. But the other thing that's important is the negative space in these materials. It's the porosity. And we're now developing strategies where we're controlling porosity down at the same size scale as the molecular building blocks. And so, this cartoon does not have a scale bar, but these holes in this obvious porous material that's interacting with the desirable molecules, those pores are on the size scale of the building blocks and the molecules themselves, or just slightly larger. And so there are many strategies that have emerged over the last couple of decades as the recognition that such precise design might be possible, right? This has become the realm of materials chemists in recent years. And there are many ways to do that, and there's likely is technology space for all the different classes of materials on these slides. Some of them contain metals, such as metal organic frameworks that really set the structure, and Professor Farha is going to talk about some of those in just a minute. Some of the materials that others work on, for example, our group mostly focuses on all organic structures, whether they are covalent organic frameworks that have long-range order and well-defined porosity, or even polymer networks that for other reasons create voids through various strategies that confer high surface areas and then ultimately the ability to function for some of the tasks that we're focused on today. These range from processable to solid state materials, and all of them can be designed for purpose. And so for the next few minutes, Professor Farha is going to zoom in on the MOFs and tell you about his exciting work in this area. So far we talked about these materials from an abstract form. So when you go to the lab, or the student and the postdoc, the visiting scholars, they go to the lab and they make them, how do they look like? They come out powder, crystalline material. You could think about them as the salt shaker or the sugar. They could be colored based on what organic and inorganic you use. But if you zoom under just a simple microscope, you could see these beautiful faceted structure. If you zoom in further using the instrumentations that Nuance have, that IMCIRC has, and now you got start seeing that structure that is rotating. This is a really sophisticated molecule that been designed in order to look like those beautiful blue crystals. But if you are a molecule and we want to capture you, so what that molecule sees when it sees those large crystals that they are on the hundreds of microns. But we've been talking about nanotechnology, and here, where most of the action for that capture or that storage is really happening in that nanoregime or these nano compartment. So even though we make these materials, hundreds of nanometers, micron size, but at the end of the day, those nano compartments, what dictates how this material works from selectivity and from storage capacity. To just give one property about some of those materials, and in particular, the metal organic framework. So this MOF here, it's called NU1501. 1 gram of this material, if you are able to unfold it, which it's very hard to do, you could cover the Ryan field 1.3 times. Just think about that. What's in that little vial? That's 1 gram of NU1501. If you are able to unfold it, it will cover more than a football field. And you might ask, and who cares? Because at the end of the day, gas molecules do not like to just empty spaces. And that's why in our labs, in the hospitals, when they use oxygen tanks, they have to use high compression in order to put enough gas molecules in those tanks for them to be used for more than just a couple minutes. Nice thing about gas molecules, they like to stick to surfaces.
That means the more surfaces you have, the higher the surface area material you have, the better capacity and for gas molecules or chemicals in general. Just an example, there is more more oxygen molecules on your hands than in front of your face right now. So that's why we want to make these materials that have these high surface areas. For the next few slides, Will and myself, we would like to give you a few examples where these materials, we think they could have a potential in solving really game-changing applications. Will talked about we want to fish CO2 from air, but he also said there is also a lot of moisture in air as well. At any given point, there is that many liters of water in air around the globe. So there is a resource of water. You know, we could go clean the rivers, we could desalinate water. I'm not saying one solution is gonna fit all. Another solution is really grabbing these water molecules from air. But then you have to design materials that they are selective for water and only water. And here at Northwestern, many teams been working together for under IAN umbrella for many years, designing these materials to do exactly that. What this graph is trying to show you, that we have the ability to design materials that can capture and release water even in areas such as the Mojave Desert down to 5% relative humidity. To me, that's incredible. That can be game changers. More importantly, a few IAN PIs with Mead Technologies, led by Honeywell. They have a DARPA program that to deliver a small gadget that has the ability to capture and release water under humidities less than 20%. And in phase one, actually the first generation device was delivered and tested. This green thing that you see on those fins, this is metal organic framework to do exactly that job. But the modular nature of this material, regardless if it's COF, if it's a MOF, if it's a amorphous polymer, at the end of the day, that modularity allow us to go from between different applications. By tuning these molecules differently, now we could actually capture a carbon dioxide molecule over water. And once again, another IAN team of PIs recently won another award from the Department of Energy to do just that.
There's another strategy to incorporate voids into polymers where long-range order is not necessary. And this potentially broadens the scope of building blocks that can be used dramatically. This kind of approach is like being very bad at Tetris. We take molecules that have a well-defined shape such that they can't pack together efficiently, and then link them into networks that then cannot rearrange their structures very easily, fairly rigid linkers as well. And one can get an amorphous polymer that also has these gaps in it and unexpectedly high surface areas. And so we exemplified this approach a few years ago and in further development ever since by creating a polymer network with permanent porosity that is derived from cornstarch or cyclodextrins, which are the blue cups on this slide, are sugars that are literally manufactured in Iowa, right next to where the corn is grown. And we cross-link those sugars into this polymer. And those blue cups are very, very incredible receptors for a lot of the organic pollutants that we really need to remove from water. So when humans interact with water, we introduce a lot of organic pollutants, things like pesticides, trace pharmaceuticals, industrial chemicals, and a lot of those have the right characteristics and the right size to fit into those blue cups. The porosity of the material allows essentially all of those to be accessible at one time. And so on the bottom left-hand corner of the slide, you can see just how fast that material in blue can remove a model pollutant, in this case bisphenol A, it hits its equilibrium binding in seconds. And so it essentially removes these pollutants on contact even faster than other high surface area materials such as activated carbon. The other nice thing about these materials is that they can be regenerated. And so we can do a simple solvent wash, recover these pollutants. In some contexts, they could even be reused and thought of as a resource. In other cases, we're just glad to have them out of our drinking water. And in particular, that work has led to our recent work in addressing perhaps the most insidious organic pollutants that we currently face, these so-called perfluorinated substances. In the media, they're often known as forever chemicals. They're known as forever chemicals because they don't break down in the environment. They're abiotic. They're used in all sorts of consumer products, packaging, fire suppression foam, in the manufacture of Teflon, many, many other cases. And so these perfluorinated substances are literally everywhere. They are in detectable amounts in the blood of every person in this room because they bioaccumulate. And now we also know that they're associated with a number of negative health effects, including various cancers, complications in pregnancy and childbirth, thyroid issues. They're also associated with reduced immunity. So what's on this slide is a way to destroy forever chemicals. And it's the reaction itself is something we discovered this year, and it's not particularly nano. But let me tell you how it relates. We are not going to take this reaction and apply it to every body of water in the world. We need to bolt it onto the back of a separation technology. So the idea here is that we need to clean a lot of drinking water. A grain of rice of this stuff will foul all of Chicago's drinking water that produces in a day. We have essentially no tolerance for this stuff. It's like the EPA this year essentially announced that we should think of these like we think of lead, as absolutely intolerable. So nano-enabled solutions where we can remove and then destroy these compounds for good are absolutely essential as we especially want to reuse wastewater that might be contaminated with lots of these things. In other work around Northwestern, Professor Vinayak Dravid has developed very, very exciting technologies under the umbrella of the IIN of really, really smart sponges. So here the sponge itself is just that, it's a sponge. But the coating on the sponge it takes advantage of some very sophisticated nanoparticles and is highly, highly tailored to a separation challenge of interest. In this case, Professor Dravid and his team were interested in catastrophic oil spills. And I think we viscerally all know that's a really bad situation and a really hard problem to tackle at scale and with the speed necessary to mitigate major environmental damage. I think you're seeing the movie loop here of just how fast these sponges absorb oil off the surface of water on contact because of their incredible coatings that he and his team have developed. And this is just a single application for these sponges. There are a number of different ways to tailor these coatings to target other things in water resources. And so in terms of the future, where do we sit now in terms of air and water security? We have a very, very well integrated and important efforts here at Northwestern. And it's important when we think about these technologies is that not only is there the basic science necessary to tackle these problems at all and discover what is possible in terms of these challenging purification, separation, and resource recovery efforts. But it's going to take materials chemists, it's going to take a lot of experiments, it's going to take a lot of materials discovery effort that is highly collaborative here at Northwestern. We've already heard a lot about how computation and big data approaches of various types can inform materials discovery and development, and that is absolutely valid here as well. And then we have the challenge of scaling, engineering to really fit some of these big challenges, finding the right small opportunities that will lead us to big opportunities, and really designing for use, such as some of Newmat's products, shown here in schematic, and some of the materials that we've made that are integrated into consumer-based water purification products. And there are many other challenges that we haven't had time to go through in this talk that we're working on and see as great opportunities for nanotechnology-related research, whether it's in nutrient recovery that I alluded to, recovering critical metals from water, removing other kinds of particulates, both from air and water, including microplastics, and then also designing things like smart fabrics that purify or protect people from really acute environments, particularly in their air. And so overall, hopefully, Professor Farha and I have convinced you that the future of this work is very bright at Northwestern, and that it really will take a combined effort like we have at the IAN to really make headway on these projects. So thank you very much, and together we'll be happy to answer questions.
So we will now take questions from the audience. Please stand up if you have a question and get closer to the microphone. Chad?
Yeah, so a very nice talk. The other thing that you have to do with it, these have to be used, I would assume, at such a scale that they not only have to be so well designed, but they have to be dirt cheap. How big of a issue is that?
I'll take that and talk about the MOFs. I think everything is relative and the scale. If you're buying everything from Aldridge, yeah, everything is expensive. You buy everything at the right scale. Zeolites, about 50 years ago, there is articles about that they will never be commercialized because they are too expensive. And we know thousands of metric tons of zeolites been used around the world. So I believe right now, for example, for certain applications like this, if it's reusable, you could manage things even in the tens of dollars per kilogram with no issues.
Yes.
About the arsenic, you said recovery of arsenic in the water. There are many countries in the world actually where the water is so contaminated. An example is Bangladesh, where countryside people are literally dying by drinking arsenic contaminated water. They have to drink water, and there is no other water. So what is, again, the follow-up the question that it has to be something which is viable, applicable, simple enough that the villagers in the countryside can operate it. Any insight into that one?
Yeah, I think I can add on to Omar's answer and address your question. Arsenate is absolutely a huge problem, especially in Bangladesh and other emerging economies. And I think that there are, in terms of addressing a problem like that on a countrywide scale, I actually agree. Like if one is going to make an adsorbent for that, there on a municipal level scale, that is a very price-sensitive market, even in the United States or other wealthier countries, but even more so in Bangladesh, for example. I think that there will be nanotechnology associated with controlling the structures of very inexpensive materials. Like you start thinking about cellulose or other biomass-derived materials that we don't necessarily look at first as super exciting technologically necessarily, but I think that that is an unmet need. I think there's great opportunities. I think our work on cyclodextrins exemplifies that a little bit. Those are not, cyclodextrin is actually a very inexpensive compound because it's made enzymatically from cornstarch. However, I think that there are also solutions that will tolerate higher price points, like Omar's example of zeolites that are used as catalysts. I think that if you make a catalyst that could somehow remove arsenic or address one of these other challenges, there you can tolerate a little bit higher value or more expensive material. So I think really addressing these challenges, absolutely. I think it's true to say that the cheaper you can make it, the more impact you can have. But just because it's expensive today doesn't preclude it from being considered.
Corey?
Yeah, so your technology, compared to the commercial resins, how good it is for water filtration. There are so many resins available.
Yeah, in terms of these cyclodextrin materials, they are commercial products. So they're in 3 products right now, and I think the market will judge them for exactly what uses emerge from them. Activated carbon is a workhorse material for water purification, and it's largely a workhorse material because it's inexpensive. It's not particularly good at most of the things it's used for, but it's cheap. On the other hand, we know it's not going to solve the PFAS problem, for example. It is nowhere near good enough for that based on what the health effects are. So it's already being replaced by ion exchange resins and things of that nature. And a lot of these materials are synthetic products that look a lot like ion exchange resins from the fundamental standpoint of the ways they're made and their building blocks. And so one would expect that they could be price competitive there upon scale up.
Thank you, Will. One more question here.
I know a lot of areas have groundwater contamination, and people historically have struggled using filter-based systems. And I've seen a lot of use of nanoparticles for in situ remediation. Is that a direction you're looking to go with these particles or no?
Yeah, I think in the context of water, there are definitely advanced oxidation processes and things that are either mediated by, right now, often by ozone or cheap oxidants, and nanoparticles and those sorts of things might ultimately serve as catalysts or be effective in some way there. That's not a personal research direction, but I think it's a perfectly valid thing to be looking at.
But at the end of the day, you can't. None of those is one solution fits all. I think the solutions need to be tailored even based on the body of the water, which region, what are you trying to pull out of the water. So we just gave a couple examples out of many from Northwestern and around the world. So yeah, thinking about what are you trying to get out of the water is just as important as which material you got to be using.
I have a question. Can you give us an idea? I think most of us know why lead is bad, why mercury is bad, but with the fluorinated hydrocarbons, maybe we're not as familiar. And so can you give us an idea, what are some of the bad things that happen when we ingest them?
Yeah, so a lot of why these things cause negative health effects are not well understood, and they're different from compound to compound. So they're actually about anywhere from 5,000 to 10,000 perfluorinated substances that have been in commercial use. So to paint them with a broad brushstroke, essentially almost all of these are surfactants. So they almost certainly accumulate either in fat or in your membranes and then change their characteristics. But I'm unaware of any study that directly correlates exactly how they biologically cause cancer, for example. So
how do we know they are harmful then?
Well, so there have been massive studies of humans and livestock and animals. So it's kind of a sordid story, because when DuPont and 3M started manufacturing Teflon, they started noticing negative health effects in the workers on their lines and terrible birth defects and things like that. They hid that knowledge from the public for a long time. And meanwhile, we're also dumping these compounds irresponsibly in the communities where these plants were located. And then farmers were noticing that all their cattle were dying strangely. And so this has been the basis for many, many lawsuits now against these companies and prompted a larger scale epidemiological study of entire communities that live near, with massive PFAS exposure. So we have a lot of data that suggests that these health effects are occurring. I'm not aware of the final connection of the molecular basis of it, though.
Okay, great. Let's thank Professor Dichtel and Professor Farha for a great presentation.